I think there was enough time for a coffee, and we are about to start our fourth session, session on hydrogen, fuel cells, and electrofuels. I will follow the same structure as was in the previous panels. So first keynote lecture, and then initial pitch of panelists, and then of course discussions and questions from audience. So our speaker today is Professor Frano Barbir from University of Split, Croatia. He's Professor Emeritus and in the same time employed as project activity leader at Center of Excellence at the University of Split. He is involved in hydrogen and fuel cell technology, research and development, engineering, application management since 1980s, working in United States as researcher manager in industry as well at universities. We also heard that he was working in Turkey as Associate Director of Science and Technology of International Center for Hydrogen Energy Technologies. His research interests are related to PEM fuel cells, heat and mass transfer in fuel cells, effects of operational conditions, performances, durability, design, and so on. And he has co-authored more than 300 papers, as well as 8 US and European patents, and a very famous textbook about fuel cells, which is translated, for example, on Chinese, Korean, and Farsi, and it's used at many universities worldwide. Currently, he's Vice President of International Association of Hydrogen Energy and Croatian representative in the States Representative Group of Clean Hydrogen Partnership. And of course, member of Croatian Academy of Technical Sciences. Professor Barbir will talk about hydrogen in transport. Professor Barbir, please.
Thank you very much. Everything here is on the slide, so I can skip immediately on the next slide, which gives the outline of my presentation. I would first like to give some history of hydrogen and fuel cell vehicles, because we can always learn from history. Then give a current status of hydrogen and fuel cell vehicles. I would like to compare fuel cell electric vehicles with the battery electric vehicles. And at the end, I will attempt to predict the future role of hydrogen and fuel cells in transportation. I think it's very much clear that a hydrogen car is also an electric car. It has an electric motor, but the energy is stored in the form of hydrogen instead of any batteries. But I should also mention that every fuel cell car actually also has batteries, so it's kind of a hybrid car as well. We can also have a hydrogen in internal combustion engines, but I think that's already passé, although recently there are some advancements in internal combustion engines, but the efficiency of fuel cell systems is higher than the efficiency of internal combustion engine. And efficiency should not be compared at the maximum power, it should be compared at the average power. And there, the efficiency is about twice as much in the fuel cell vehicles than in internal combustion engine. So most of the recent developments are in the fuel cell electric vehicles. Now going back to history, the first hydrogen car was developed 1807, and it was in France. This vehicle used the first internal combustion engine that used hydrogen as a fuel, and hydrogen was stored in a balloon. And this vehicle is now in a museum. And then a few decades later, the fuel cells were invented. Actually, the Swiss-German scientist Christian Schönbein is the first one who realized the fuel cell effect, and he was in communication with Sir William Grove as well as with Faraday, and those letters are saved, and they prove that Schönbein is actually the one who first observed the effect of fuel cells, but the Grove was the one who first made a working fuel cell and applied for a patent. Then again, several decades later, we have a remarkable prophecy by Jules Verne, who made many predictions, and many of those predictions came true. And so this one about hydrogen being a fuel of, or as he said, water being a fuel of the future with its constituents, hydrogen and oxygen, is also coming true. For me, another remarkable prophecy is by Friedrich Wilhelm Ostwald, who is a father of physical chemistry, who also more than 140 years ago realized that the energy conversion in combustion engines is limited by Carnot efficiency, thus has a very low efficiency, and creates unacceptable levels of atmospheric pollution, unlike the fuel cells that are direct generation of electricity, highly efficient, silent, and no pollution. He predicted that transition would be a technical revolution, which we are starting to see now, and the prediction was the practical realization would take a long time, and indeed, it took now more than 100 years. Between two wars, there was a lot of development of hydrogen vehicles by a German engineer, Rudolf Ehren, who worked both in Germany and UK, and he also has some patents in the United States. He made dozens of buses and trucks running on hydrogen using internal combustion engine. And then in 1993, Norsk Hydropower Company converted one of their small trucks using hydrogen engine, but the hydrogen was not stored on board. It was ammonia that was stored on board, and there was a small ammonia cracker on board the vehicle. And then about 100 years after the fuel cells were discovered, we had the first practical fuel cell. It was by Francis Bacon in UK, and that was just before the Second World War. And then after Second World War, this technology was obtained by a US company and used in a space program. But this was the first fuel cell system. And then very soon after, we have a first fuel cell vehicle. It was Alice Chambers' farm factor that was developed in 1959. This tractor is now in Smithsonian Institute. And then we have a space program where they use not only hydrogen as a fuel for propulsion, they use fuel cells in both Gemini and Apollo program. And what is interesting, in Gemini, they use PEM fuel cells, which are now actually predominant type of fuel cells. But at that time, they were not very reliable, so they switched to alkaline fuel cell based on Francis Bacon invention, and they use them both in Apollo and Space Shuttle. And that was actually the beginning of a new era in development of fuel cells for practical Earth applications. First, in 1966, General Motors developed this van, which is considered the first fuel cell power vehicle. And then Professor Carl Kordesh, who at that time worked for Union Carbide in the United States, converted this car. You can see the hydrogen tanks on the roof. It looks funny, but he used this car for 3 years for commuting, going to work, back and work in Boston. Later, he came back to Austria and was a professor at the Technical University of Graz. And in 1993, a Ballard company, which is now a well-known fuel cell company, created a fuel cell bus. And just about a month later, a company in Florida called Energy Partners made the first PEM fuel cell power passenger car in the world. I'm proud of this because I was a part of this team that developed this car, and you can see me this in the middle of this, look at this tall guy in the back with a mustache and with the black hair. By 2000, every car manufacturer has developed at least a prototype, and some of them even a fleet of vehicles. And then in 2014, I was in, I think, medical waiting room waiting for a doctor, and then I passed through those magazines, and one of them was Popular Mechanics, and in that there was an advertisement for Hyundai. That was 2014, and the title was the first mass-produced hydrogen car. So Hyundai actually started selling those cars in Korea. A year later, Honda was leasing these cars in California. It was called FCX Clarity. Mercedes had developed even before Series B in a small production. They had a world tour with these cars. And then in 2017, they came with the idea of first a plug-in fuel cell vehicle, which does make sense, but they actually never realized this because in the meantime, they changed the CEO and they changed the policy and the strategy. So the first commercial fuel cell car is Toyota Mirai. Mirai in Japanese means the future. So this is the car of the future that Toyota developed. Ankita will later show you some more of this picture. This is the newest model of Mirai. They have a business model selling cars not only to individual customers, but also to the taxi fleets, for example, in Paris and in Hague. I had a chance to watch a video on YouTube about a taxi driver praising this car. He said this is much better than the batteries for, if nothing else, than for a very fast refueling. He said, I spend only 5 minutes to refuel my car and I'm back on the road with the customers. And the newest model is again Hyundai Nexo, which is also being sold in Korea, and later you will see the most cars now in the world are sold in Korea. So this was taken from a magazine, the hydrogen cars in 2023. There are only 2 listed. So there are basically 2 car companies that are selling fuel cell cars. If you want to buy a fuel cell car, you only have 2 options now, which is a Toyota Mirai and Hyundai Nexo. And the price is about $60,000, and they are even rated here on the right side. But recently, earlier this year in May, we had a conference here in Zagreb organized by Ankita, and there was a BMW with a new car, iX5, and they are entering in the low volume production. I had the chance to drive this car. This brings us to comparison between electric vehicles with the fuel cells and those with the batteries. Yesterday we heard several times the battery cars are much more efficient than the fuel cell cars, therefore we should use electric cars with the batteries, not the cars with the fuel cell. And there is no question about it. The batteries from well to wheels about 70 to 90% efficient. The fuel cell cars about 30 to 40% efficient. So there's about 2 to 3 times more efficiency if we use batteries instead of fuel cells. But efficiency is not the only criteria that we should compare the cars. There are many other things that the final customer will actually decide on. For example, refueling time. The fuel cell car can be refilled in 3 to 5 minutes, while the battery car can refill about an hour or more. Then energy density in terms of size and weight. Hydrogen itself has about 40 kilowatt hours per kilogram, but efficiency of fuel cell is about 50%, so we get about 20 kilowatt hours per kilogram electricity. If we include the tank itself, we come down to 0.7 to 0.9 watt hours per kilogram, because in the hydrogen tank we only have few percent of hydrogen by weight. And if we include the fuel cell itself, then it's about 0.4 to 0.6 in the present systems. In the present systems, the batteries are 0.1 to 0.26, the highest one I saw on the market. So there is an advantage again of 2 to 3 times in terms of gravimetric power density in favor of fuel cells. And what is important there is a separation of power and energy. In the batteries, power and energy are in the same device. In the fuel cell, the power is in the fuel cell and energy is stored in the hydrogen. So if you want to extend the range of these vehicles, you don't have to add more fuel cells. You add just more tanks. And those tanks have a gravimetric power energy density of 0.7 to 0.9, which is 5 to 6 times more than the batteries. So the larger the vehicle, the more energy you have to store on vehicle, the hydrogen becomes better and better. But then again, there are many other things that should be compared. Safety of fuel cell vehicles and hydrogen, and safety of batteries. There are very few studies about this. Usually, the researchers and the companies don't like to publish papers about failures, but there are failures of, I've seen the fires of batteries, I've seen the fires of hydrogen vehicles, so that has to be studied and published also. There is a performance in extreme conditions, extreme heat, extreme cold. There is also performance loss over time and durability of both fuel cells and the batteries. And there are, we heard also yesterday about the materials constraints and the recyclability that applies to both the fuel cells and the batteries. But finally, the owner or the potential customer will make his decision basically about the cost, and that's a lifetime cost, not just the purchase of a vehicle, but also a lifetime operation and the cost. Automotive companies are making their plans for the future, and usually they make maps like this. I believe this is a General Motors about 10 years ago, and they believe that the battery vehicles will be for small vehicles with a light load and a short driving, but for a longer driving and a higher load, the fuel cells becomes more and more interesting. There is a similar slide by Toyota, but I'm pretty sure that Ankita will have this slide as well that shows the same thing. So on one side we have a traveling distance, on the other side we have a vehicle size, and you see that for a short distance and small vehicles, batteries are better. For higher, the fuel cells become more attractive. Besides the passengers, that becomes more attractive for the buses. This is a chic program that was running between 2010 and 2016 in Europe, and there was also 10 buses in Canada. Overall, 26 buses were tested in 7 EU cities. This program was continued with the 3 Motion, where another 29 buses were tested in between 2015 and 2022. And then the program Jive 2, and the Merlin tested both the vehicles and the infrastructure. Excuse me. And we had an opportunity to test one of those buses here in Zagreb. In December, we had one Caetano bus that was used by ZET, the Zagreb Public Transit Authority, and it was tested on the routes that are extremely difficult, for example, for batteries going to Sljeme and going back, and they were testing the hydrogen consumption. There was also a refueling station improvised in their facility in Podsused. And then there are plans for additional 1,000 hydrogen fuel cell buses along with the supporting infrastructure in European cities. And these numbers are still not high as they should be, because you should know that China is producing 1,000 fuel cell buses a year, and we are talking about here in a 5-6 year program in Europe. So we are lagging behind. I had a chance to work on one of these projects on a fuel cell bus. We were actually developing the fuel cell range extender to the battery electric bus. Company was VDL, the largest manufacturer of electric buses in Europe. And we were quite successfully built this system. It was led by Bosch and Erwin Klinger. And by the time we were making these pictures, I was strolling around their yard, and I noticed those trucks. Those were DAF, label was DAF, and they were hydrogen trucks. So the same team that was working on this project was also working on these trucks. And the team from Bosch, after this project was over, they flew to Arizona because Bosch bought shares in the company called Nikola that is making hydrogen trucks. And this left picture is from May 2018, when they announced that they have ordered for 800 hydrogen trucks. And just last week, actually yesterday, I found this on internet, that Nikola's landmark launch of its hydrogen fuel cell trucks in North America. And it's not just the trucks, because you can build as many trucks as you want, but if there is no refueling infrastructure, that's useless. So I know that Nikola was also working with my ex-company that I work for, Proton Onsite, which has been bought by Nel, now on establishing at least 200 refueling stations along the United States. Hyundai also came with a fuel cell bus and claiming they have a customer in Switzerland who ordered 1,600 trucks. A similar announcement came from a company called Hyzon. When I checked this, those are mainly ex-General Motors engineers. They have order of 1,500 hydrogen fuel cell trucks in New Zealand. But the big players like General Motors are also developing a heavy-duty hydrogen fuel cell truck, Volvo as well. And then again, recently they made an announcement that the customer testing will start in 2025. But on this slide, we have American company Kenworth working together with Toyota. They already have trucks ready for the road. And no wonder the trucks are actually more successful, because this study performed for the Clean Hydrogen Partnership showed that the hydrogen buses, and those are those with the blue lines here, are very much cost competitive, and cost means the total cost of ownership with the other technologies, and also very close to the existing diesel buses. And in 2027 and 2030, they are even the least expensive option. So to summarize the latest news on hydrogen vehicles, you can find any information on Google and internet today. So the number of fuel cell vehicles in the world increased by 40% only in 2022, totaling to 72,000 vehicles. About 20,000 vehicles were sold in 2022, and only 15,000 of them were cars, and 2/3 of these cars were sold in South Korea. About 80% of the global stock are cars, with 10% being trucks and almost 10% buses. The fuel cell truck segment grew at a faster rate than the cars and the buses, increasing by 60%. And what is interesting, China is home to more than 90% of the world hydrogen trucks and almost 85% of the global fuel cell bus fleet. And there are about 1,000 hydrogen refueling stations in operation around the world, and about 200 in Europe. Hydrogen is also very interesting for the trains. There is a Alstom train that is running in northern Germany. It's actually in service already, and the Siemens is also developing excuse me, a hydrogen train. For 2 weeks ago, we had a conference in Zagreb here about hydrogen on trains in Croatia, in the Ministry of Sea and Transport and Infrastructure. And the purpose of the conference was we have in Croatia opportunity to use such trains because these trains are especially cost competitive on non-electrified lines that are longer than 100 kilometers, and they have less than 10 trains traveling on those. And we have such a line between Zagreb and Split, actually between Ostarije or Ogulin and Split, that is not electrified, and it will never be electrified. So there's an opportunity for Croatia as well. I did mention hydrogen refueling stations. There's about 1,000 of them in the world, 200 in Europe. Those are pictures of some of them. And this is a map of how many are there in Europe. I said about 200 so far. And that brings me to the study that was performed by Jülich Research Center in Germany that compared the infrastructure of batteries and the infrastructure for refilling the hydrogen. And the conclusions actually show in this picture below, and shows for a low volume, the battery infrastructure is cheaper because it relies on existing power plants and existing lines. But in the future, for the same amount of vehicles on the road, the fuel cell actually infrastructure may become even cheaper. And here are some of the conclusions of this study. So for low market penetration levels, a few 100,000 vehicles, the cost of infrastructure low route are essentially the same for both technology. Hydrogen infrastructure is found to be more expensive during the transition period, but for a high market penetration up to 20 million vehicles, a battery charging infrastructure would be more than a hydrogen infrastructure. The mobility costs per kilometer are roughly the same in the high market penetration scenario. And for the scenario with 20 million fuel cell vehicles, approximately 87 terawatt hours of surplus electricity for electrolysis, and the emphasis here is on the surplus, plus 6 terawatt hours of grid electricity for transportation are required. On the other hand, charging 20 million batteries electric vehicles accounts for an electricity demand of approximately 46 terawatt hours out of the distribution grid. And then also, while preparing this presentation, I came up to this study that was performed just last year that tries to, for me, very realistically estimate the effect of batteries and fuel cells. And on this small graph here, you see actually these are the existing vehicles, and then the batteries are light blue and the fuel cells are dark blue. So small percentage of vehicles on the road will still be fuel cells. And it will take me more than allowed time to actually explain all these graphs too. But the conclusion of this study, we need both infrastructures, and it'd be cheaper to have both infrastructures just to try to have just one of them. So coming to conclusion, there are issues with hydrogen for transportation. First of all is competition with batteries. But for me, actually, there is no competition. There should be actually just market sharing. Different market segments can be covered by batteries. Different market segments can be covered by hydrogen vehicles, because hydrogen fuel cell electric vehicles have three major advantages that I already mentioned. That's a separation of power and energy, gravimetric specific energy, and a fast fueling. Also, the other issues that are actually preventing a large-scale hydrogen deployment is a hydrogen production from excess renewables. Hydrogen makes sense if it is produced from excess electricity. And we heard also yesterday there will be a lot of excess electricity once we go to the 100% renewable energy systems. We will need 2 or 3 times more installed power than what we actually need to satisfy just the power requirements, and that excess should be used to produce hydrogen, and that excess, of course, will have a very low price. So that will also reduce the price of hydrogen, because right now hydrogen is relatively expensive. And of course, there is no enough infrastructure, because we still have there a chicken and egg problem. Nobody wants to build a hydrogen refueling station, because in order to be commercial, they need at least 200 vehicles on a daily basis to fill the hydrogen there. And nobody's going to buy a hydrogen car because there is no hydrogen infrastructure around. And then at the end, I promise I will attempt to predict where hydrogen and fuel cells offer sufficient advantage to make significant contribution to decarbonization of transport. However, I have a warning here, because predicting the future is a risky business. This is how 50 years ago the scientists from a Rand Corporation envisioned the home computer will look like in 2004. And we can now all laugh. So I don't want 50 years later people laughing at me and say, Professor Barbie said in 50 years we will drive hydrogen cars such and such. And also there are some other remarkable prophecies here by experts at that time. IBM chairman said that he thinks there is a market for maybe 3 computers in the world. And the president of Digital Equipment Corporation in 1977 said that there is no reason why anyone would want to have a home computer. They couldn't be more wrong. So I hope with my prediction I will not be that wrong. So my prediction is that the cars, hydrogen will be used only for those customers that find fast fueling important. Buses depend on the route configuration, available time for refueling and recharging. For example, the route that goes uphill, the hydrogen is probably better than the batteries, because the batteries will be empty by the time the bus reaches top of the hill. Similar goes with the trucks, or depending on the route length and the configuration and available time for charging or refueling. Trains, probably for regional trains on longer non-electrified routes, as I already explained. I didn't touch ship and ferries, and I believe my colleague Rodolfo Taccani will talk a little bit about ships and ferries, but only for shorter routes. For longer routes, probably ammonia or some other e-fuels will be better. And for airplanes, there is still discussion. There are studies from back in the 90s, and there's a recent one by Airbus, and before was by Boeing. Hydrogen is the lightest fuel of all. It's 3 times lighter than other fuels, so that's very alluring for aircraft. But hydrogen tanks are heavier, so at the end, the hydrogen may be heavier than other fuels, but it certainly is very attractive fuel for airplanes. And the last, so I predict that the priorities for decarbonization of transport should be, first, electrification with batteries or catenary. Hydrogen will be used in segments where electrification is not possible or feasible, or where hydrogen offers some other advantages or convenience. And at the end, e-fuels produced from hydrogen, because don't forget, e-fuels are produced from hydrogen. So if you use the argument that hydrogen vehicles are less efficient than the battery vehicles, then we should also use the argument that e-fuels are less efficient than hydrogen, because e-fuels are produced from hydrogen. But there are still segments where hydrogen is not possible or feasible, and where the e-fuels may offer other advantages, such as, for example, in ships and airplanes. And with that, I would like for your attention and draw your attention to my recent book that I just got a copy before I came here to Zagreb. It's called Fuel Cells for Transportation, exactly as the title of my presentation here today. Thank you very much.
Okay, thank you very much, Professor Barbier. So we will have enough time later on to discuss about open questions. So our next panelist is Professor Tomasz Katrašnik. He's full professor of energy engineering at University of Ljubljana, Slovenia, and scientific counselor at National Institute of Chemistry at the Department of Materials Chemistry. He's also head of the Slovenian research program Energy Engineering and president of Technical Board of Slovenian Strategic Research and Innovation Partnership Mobility, as well as leader of Sustainable Energy pillar of Slovenian Strategic Research and Innovation Partnership for the transition to circular economy. His research is focused on multi-scale modeling of batteries and fuel cells, as well as on electric, hybrid fuel cell and conventional powertrains, internal combustion engines, thermochemical processes, alternative energy vectors, and so on. So, Professor Katrašnik, please give us your initial pitch.
Good morning to everyone. Thank you for the invitation and thank you for the introduction. So since I knew that Professor Barbier will address this topic very holistically, I will then just focus on one smaller part, which is the role of advanced observers in maximizing performance and safety of fuel cell systems. So Professor Barbier already talked in general terms about this. So there are also some safety issues, durability issues. And let's say, if we look now to such a let's say, renewable energy system. So we can see here, let's say, fuel cells, electrolyzers. So I will today talk about the fuel cells, but the same is valid for electrolyzers. If we go further, we can see that there are some electric vehicles connected, so fuel cell electric vehicles connected to it, sorry. And if we then dig into it, in the fuel cell electric vehicle, we see fuel cell stack. In a fuel cell stack, we see a fuel cell single cell with channels. Here you see membrane electrode assembly. And if you go deeper in, you then see membrane catalysts, and already here we are on micro or nanometer scale. And fuel cell works only if all these processes and all these scales work properly. And certainly, which is unfortunately the case, the fuel cell is, except for first few moments, all the time when it operates, dying. This does not mean that it's useless, by far not. This just means we have to take care how we operate it, and we have to know what happens inside. And as said, to master this, we need to cross much more scales, let's say, that were previously encountered in transport with internal combustion engines. And so, why this is so important? Let's say this is some basic graph. You see steady state operation, so this is fuel cell degradation, so performance degradation, and you see here various transient operating conditions. And so you see that various transients decrease significantly the lifetime of a fuel cell, also potentially its safety. And the harsher the cycling, the shorter its lifetime, and it's also depending on the profile. So idea is, if we want now to maximize return on investment or durability or use minimum of precious material, it's not just important to produce a cell, but it's very important how we operate it. Therefore, also we have in fuel cell electric vehicles the battery, that we minimize this phenomena. So how it degrades. So these are now really atoms. These are a few sketches. Let's say we have some carbon surface oxidation, so where the catalyst is on carbon support. Platinum can dissolve. It can go from small particles to larger particles. You see here we can burn off carbon support, and also the membrane can be attacked from some radicals, just to name a few of them. Then if we look on slightly bigger scales, we are still, you see in 100 nanometers, you see here cracks. So here is the membrane, here is the catalytic layer. It might crack. We might get pinholes, and this is then already a safety critical event. At the end also, since all particles grow, we will have less platinum, we will have lower performance, fuel cell will produce more heat, and then certainly we should identify this. And then basic ideas are now in the cars. So here's a car, we will have kind of fuel cell management unit, which is currently not that complex, but it will get more complex in the future. And here are these advanced observers and virtual sensors. Why they're important? Because we cannot install all physical sensors, but we still want to see in the fuel cell. And what we need for this, so we need physics-based or mechanistic models, we need some observer frameworks, and we need then parameterization tool. We have to identify if we have well parameterize it, and we have some model-based DOEs that we can really look competently into it. And yes, all of a sudden we are then talking a kind of digital twins which will run with us. Some of them will be on a car, some of them will be on a cloud. So this is still currently under development. And let's say how it will look like at the end is that we will have real unit under test. We will have some inputs, and in parallel, models will run, which will compare outputs of real system to outputs of the model. And with this, then we can do a lot of identification and see what's happening. So here, I will only show some brief results, and with this I will end. So these are the values that were measured in Professor Barbiro's lab. So you see here, quite heavily degraded fuel cell. Then we put a model on it, we parameterize it, and then all of a sudden we can look inside the fuel cell. You see, we can see how much the intrinsic exchange current density has changed, how much ohmic resistivity, how much diffusivity. So this gives us the quality of the catalyst. This gives us information on the membrane. This gives us information on the GDLs. And yes, we have also validated this, and you see the model prediction coincides well with what was then experimentally measured. And here, the main message is that advanced model-based control monitoring, and in particular diagnostics, which is not yet developed very well, is key to ensure high efficiency and durability of electrochemical devices, fuel cells, electrolyzers, but the same is also valid for batteries. So for greening, we also need a lot of digitalization. So thank you.
Okay, our next panelist is Professor Rodolfo Taccani. He's Prorector for technology transfer at the University of Trieste, Italy, and full professor of power plants at the Department of Engineering and Architecture. He was president of the Italian Thermotechnic Association since last year, and his research interest comprised the analysis and optimization of energy conversion systems with particular reference to fuel cells and hydrogen. Currently, he is a member of the joint working group of the North Adriatic Hydrogen Valley. So, please.
Thank you very much for the presentation, and thank you very much for inviting me for this opportunity to give this presentation. Well, I want to start from something that Professor Barbier said earlier, and in particular that to increase the number of hydrogen or green vehicle, we need an infrastructure. We need more green hydrogen, and we need to reduce cost, because today we know that hydrogen is very expensive. So for this reason, one reason that in our macro region, I'm talking about Friuli Venezia Giulia, Slovenia, and Croatia, the Hydrogen Valley was started, the so-called North Adriatic Hydrogen Valley. And I will tell something about this Hydrogen Valley. So a way to develop an ecosystem for the complete value chain of green hydrogen. But 2 words about the University of Trieste. So maybe some of you knows already, it is a medium-sized university with about 20,000 students. But more than this, it is part of the scientific and innovation system of the Friuli Venezia Giulia, a network of 17 research institutions with the aim to boost the result of scientific research in terms of socioeconomic benefits. What is the Hydrogen Valley, the North Adriatic Hydrogen Valley? It is an hydrogen valley that encompasses 3 territories: Friuli Venezia Giulia region in Italy, North Italy, Slovenia, and Croatia. In particular, one of the first steps of this hydrogen valley ecosystem is the development, a proposal submitted to the European Horizon calls that was successful and started in the 1st of September. So we have now a Horizon Europe project running with the same name, North Adriatic Hydrogen Valley, that encompasses 27 partners, 5 research institutions, and 3 public institutions. And the overall value of the project is about 350 millions of euro. Well, as I said, an hydrogen valley includes regards all the value chain of green hydrogen, starting from green hydrogen production, for example, from photovoltaic, from wind turbine, then transformation of green electricity to green hydrogen, and utilization. And this is an important aspect of an hydrogen valley. So utilization is not only for mobility, but it is also for industrial processes, for the so-called hard-to-abate sectors, such as steel industry, cement industry, glass industry. And then we have let's say, heat and power application and mobility. Mobility, but as Professor Barbier said, where fuel cell and hydrogen finds a better way of utilization, it is probably the so-called energy-intensive mobility, such as trucks, as we saw before, and shipping, propulsion of ships. And this is what I will address a little bit more in the later. Well, just to say that this North Adriatic Hydrogen Valley was quite a long process to establish this ecosystem, and because it was recognized by the public institution. And it was, in my opinion, a perfect example of international, of transnational collaboration. As you see, here are the territories involved. In particular, what you see here, there are the pilot project of the European project, of the Horizon Europe project only, and there are other projects that will be developed. But these that you see here are the demo case of the European project. The way of transportation of hydrogen will be mainly compressed gas, but it will be also studied the possibility to transport the hydrogen in liquid form and through a pipeline. But what I want to point out is that our territories are on the sea. So shipping is one key aspect in Italy and in Croatia. So therefore, part of the project, and here is the list of the pilot project that will be activated in this Horizon Europe project, regards also shipping, propulsion of ships with hydrogen and fuel cell. Well, one of the projects that will start first, it will be a green hydrogen production plant in the port of Trieste. And again, the application of hydrogen for green shipping is coming out. It will be a 2.5 megawatt electric electrolyzer, and the electricity will come using a photovoltaic plant with a peak power of 4.5 megawatt. And also part of the waste treatment plant electricity that is coming out from burning, from oxidizing the waste of the town, will be used also to produce hydrogen. And as you see here, this Hydrogen Valley project regards the utilization of green hydrogen for the industry, for the hard-to-abate sector, but also for transportation, and in particular, as I said, for high energy-intensive transportation, such as trucks and shipping. Why shipping? Because shipping, we know that it produces about 3% of the total greenhouse gases overall. So it is not a big amount, but it's very concentrated in coastal area and in particular in ports. So you can imagine a big ship that is entering the port of Dubrovnik, for example, of the port of Trieste, has an installed power of tens of megawatts. So it pollutes as 1,000 of cars. So the idea, and here I am presenting just as an example of some of the projects that, let's say, the Friuli Venezia Giulia side is carrying on utilization of hydrogen in shipping. So if we can decarbonize shipping, we can actually improve the quality of the coastal area. But as we saw earlier by the presentation of Professor Barbier, the internal combustion engine has a low efficiency for small installed power, for part load operation, but in the case of ship, an internal combustion engine of a bigger power output can have an efficiency up to 50%. So you see that the fuel cell can be competitive, but there is not a clear, let's say, clear winner of if the engine is a fuel cell or it is an internal combustion engine. So therefore, this is one of the key aspects together with the hydrogen containment, and we are thinking about other hydrogen carrier, for example, methanol or ammonia. So in the future, it is very, as Professor Barbie said, it's very difficult to see, to foresee who will be the winner. But anyway, the International Maritime Organization set a clear limit in the emission of shipping as well. So we want in 20 years to go almost to zero carbon emission in shipping. So in the next year, it will be very interesting to see what will be the technology development. But by sure, electrification and utilization of hydrogen also in shipping, especially in short route, will be interesting to keep under consideration. Thank you very much.
Our last but not least panelist is Professor Ankica Kovač from University of Zagreb, Croatia. She's head of Power Engineering Laboratory and founder of Regional Hydrogen Energy Conference, as well as the editor in the International Journal of Hydrogen Energy. She designed the first Croatian hydrogen-powered bicycle and installed the first Croatian hydrogen refueling station. She worked a lot on the advertising of hydrogen transportation, and together with company Toyota, she organized the Croatia Mirai Challenge as the road trip from Zagreb to Brussels. Professor Kovač is member of the executive committee of the collaboration program on advanced fuel cells, where she is official representative of the Republic of Croatia, and also she is member of the council of the president of the Republic of Croatia for energy transportation and vice president of Croatian Hydrogen Association. So please.
Hello, everyone. Good afternoon. As you heard, I'm from University of Zagreb, Faculty of Mechanical Engineering and Naval Architecture, where I'm a leader of Hydrogen Group, and we are working amazing things, and we are involved in amazing projects. But today, on behalf of Managing Director Krešimir Bago, I will give you a short overview of Toyota Croatia, and not just Toyota Croatia, but Toyota in a global. Why we are all here? I think we are all here and we are discussing about transportation, and not just about transportation, is a climate change. Climate change is the most important question of our era, and we need to focus on solving this issue. And I think we are all on the good path, not just in the carbonization of transport, but on the carbonization of all sectors, and on involving new technologies wherever we need and we can. So it is important to speed up the process and to use all technologies without CO2 emission, and to not take them about competitors, but to take everything we have on the market to reach our goal of climate neutrality by 2050. So what does Toyota work? Well, Toyota gives a huge effort on the decarbonization of transport, and not just in their own company for producing vehicles, but also for producing fuel cells in collaboration with other companies for the tracks and for backup systems at some large data centers. So Toyota has started very early. We have their work in dating up from 1992, where Toyota started to work on a fuel cells and on this technology. And today we already have a second generation of Toyota Mirai. And here in Croatia, we had a great opportunity to host first generation during our Croatian Croatia Mirai Challenge, as we heard, a road trip from Zagreb to Brussels. And also last year in November, December, we had the opportunity to host Toyota Generation 2 and also Caetano bus where Toyota worked with Caetano in developing this bus. Toyota has a multi-tech approach. Their opinion is that there is not only one solution. As I had already said, we have to take everything good that we have on the market and to use it for higher goals. So they have fuel cell electric vehicles, hybrid electric, plug-in hybrid electric, and also battery electric. As we already saw this sketch, Toyota Sustainable Mobility Strategy is developed globally, and depending on the state, on the requirement, they offer on the market the solutions that state required. They are very much focused on building a hydrogen society. That is our common goal in global. There is often a dilemma that we are talking about when we have some discussion about what was the first hydrogen vehicle or what to build first, hydrogen vehicle or hydrogen infrastructure. These two technologies has to go together. So by involving hydrogen vehicles, we in parallel have to work on introduction and installation of hydrogen infrastructure to supply existing vehicles, personal vehicles, trucks, trains, or whatever we have. So we have to go together all of these technology so we can put everything on the market. That is why Toyota developed a one-stop shop model, so bypassing capex for cities they are collaborating with numbers of partners on different stages. So it is not just the point to buy and pay for the vehicle, but there is behind the whole strategy and technology and a lot of work. So we can drive on hydrogen in transport, in industry, or wherever we want. Public transport is a hot topic, and many cities are working on introduction of hydrogen fuel cell buses. Today we have cities that already have in commercial use hydrogen buses, but numbers of them are promoting clean transportation based on hydrogen. Toyota is a part of this project in different cities across the Europe, and also Zagreb had the opportunity to host hydrogen bus in November, December last year, we had the opportunity to be a part of this unique project across the Europe, and to test hydrogen buses in all of our environment. So we also went to Sljeme, and it was amazing. It was snowing, and I think the best photos within this project, Jive 1 and Jive 2, has been sent from Zagreb because of the atmosphere. You have snowing, and you have a fuel cell bus, and you really have a feeling that you are doing a good thing. So you are driving in, you are a part of transportation, but without pollution. You feel on peace. I'm clean, my environment is clean. I think it is a really good feeling. Thank you very much.
Yeah, I would like panelists to join me here. Yeah. Hydrogen is really nice, but I would like to start with safety. So Professor Barbier, just point out few, let's say few words about safety. What are issues?
For leak of hydrogen is the highest among all the fuels. But the consequences of that leak are probably least than other fuels. So in many aspects, hydrogen is, I would say, at least as safe as other fuels, but in some aspects even safer. And if you click on the internet looking for the hydrogen safety, you can find the photos of back in the 1990s when I was doing my PhD at the University of Miami. Professor Mike Swain was doing with his group a safety test, and he had a force focus with gasoline and force focus with hydrogen. They drilled a hole in a tank, both of hydrogen and the gasoline, and they ignited and both it, and then they filmed everything. And you can see those films there. The gasoline car, because gasoline is heavier than air, gasoline goes on the floor, and when it ignites, the whole car was in flames. But the hydrogen flame from the tank went straight up, and it lasted 90 seconds, and after that it was extinguished because there was no more extinguished, and there was no more hydrogen in the tank, and the vehicle was safe. Interesting, this 90 minutes, because anybody knows here about the Hindenburg. Nobody's alive here when Hindenburg happened. That was in 1937. But that is actually proof how safe hydrogen is, not how dangerous. People use this to show how hydrogen is dangerous. First of all, that didn't explode. Second, hydrogen was not the cause of fire. The fire was caused by the lining on the Hindenburg. And when the fire happened, of course, hydrogen ignited, and the flame lasted 90 seconds. And it was long as 3 football fields full of hydrogen, and after the fire was gone, it went down. And 62 people survived this accident. 30 people, I think 32 died. Some of them died because they jumped from the gondola, and some of them died because they were close to the mechanical room that used diesel fuel. That ship used diesel for the fuel. So that's actually an example how safe hydrogen is. There are several features that I can talk hours and hours about the safety, but hydrogen is at least safe as other fuels. That's what I would say.
Thank you. Let's move on the common things which are related with use of hydrogen. Let's say so, storage, transportation, production. Can you give a comment on it? I think the part of this initiative in North Adria was related to the transportation by pipelines. So how efficient is transportation by pipelines in comparison with other kind of hydrogen transportation?
Thank you. Yes, transportation of hydrogen is still a complex and difficult challenge, because as you said, transporting hydrogen costs energy. So even if we compress it or we transform it in liquid form, it is part of the energy content of hydrogen is lost in this process. Just to make an example, to compress hydrogen in a pressure vessel up to 300-400 bar, we lose, depending on the type of compressor or the process, 5% of the total energy that we store. And at the same time, if we want to liquefy hydrogen, we lose 20% of the energy. So the problem of transportation is very complex. One way is pipeline, and we know that in Europe we are talking about that. In Italy also, and there are feasibility studies to transport hydrogen together with the natural gas in the pipelines, but up to a concentration, not 100% today. So today, for example, according to the SNAM, that it is the company that transport natural gas in Italy, the percentage of hydrogen that we can put in natural gas is some percent, up to 10-20%. But again, we have a fuel that contains carbon, not only hydrogen. So the next frontier is to develop pipelines for pure hydrogen, but this is something that has to be done from the very beginning. At least to the knowledge we have, one pipe that is used for natural gas cannot be used today for transportation of pure hydrogen. Therefore, the transportation of hydrogen remains a big issue, and therefore other way of transporting hydrogen with hydrogen carrier is under investigation.
Okay, thank you. Professor Katrashnik, let's move to the start, hydrogen production. So you was talking about problems with catalyst, platinum, and so on. What is the current research on different materials? You are working in the Department of Materials Chemistry. Is there any way to supplement material which is used in fuel cells? And is there any other ways to produce green hydrogen, for example, dark fermentation or biological processes? What is about these technologies and what is the state of the art?
Thank you. Very complex question. I would dare to say that, currently we have many technologies to produce hydrogen. Also, if you go to electrolysis, you don't have only one technology. Let's say it could be solid oxide, you could be a PEM. The challenge is, as low as you stay in a low temperature, which means smaller units, which means units that are not fully transient capable, but more prone to cycling, you are then currently still non-platinum based catalysts do not yet perform well. So you're stuck with precious metal, whose price is quite high. If you go, let's say, already to solid oxides, certainly they are not all abundant materials, but at least you have no presence of platinum, which already quite significantly decreases this pressure. But yes, as you said, electrolysis is maybe currently the main source of hydrogen, because we start with green electricity. And so this is how also comparisons that Professor Barbie was addressing start. So we start with electricity, or in the future green electricity, and then we compare. Certainly biological processes are competitive, and I think also they will be in the future for sure have some market share. But let's say at least if there would be no breakthrough in technology also in this area, currently, if we look in overall energy demand, not only for transport, but overall, it does not seem to be feasible that we will be able to produce a very significant amount. So take saying half of this energy by biological processes, but this does not mean that a significant share, or the share that we can maximize, should not be exploited. And I'm very much looking forward to also these alternative processes. And also in that respect, also the hydrogen as an energy vector, I think it's for sure a viable one, but also due to the fact, as Professor Barbier addressed, on one side there are, let's say, if you have transportation batteries, on one synthetic fuels, there is for sure a share for hydrogen, but since we have three competing processes, it's maybe less well defined for now, because also the infrastructure is not there. But therefore, I think it's really important that we come up with the production of green hydrogen, which then also boosts LCA analysis. And also, as said, if we don't go for hydro energy, which is storage and green energy at the same time, but if we go to solar panels, wind energy and others, for sure, we already now see negative prices of electricity, or let's say we disconnect solar panels and stuff like this, which is from an energetic point of view not reasonable. And if this part of this energy, or higher share of this energy, would be stored in hydrogen, this will also have economical effects and economy of scale effects and stuff like this. But I think this is now really ramping up. Europe was, I think, stacking behind Japan and China, but with now all these projects on hydrogen valleys, research projects, start of productions of fuel cell vehicles, I think we will now get momentum in this area.
You notice that in the North Adriatic Hydrogen Valley, we have at least 3 projects that intend to produce hydrogen from waste. So that's also, waste is not renewable energy per se, but it can be provide additional amounts of hydrogen, because that solves 2 problems. In Croatia, we didn't solve the problem what to do with the waste, and now we can solve the problem with the waste and also with hydrogen. And there is also another possibility, not to use the noble metals like a platinum, iridium, but there are also electrolyzers that can use other catalysts, and Ankita can tell us for alkaline, they can use nickel. Yeah. So there is, we are not limited only to platinum.
Okay, thank you.
Professor Kovac, what is with infrastructure? So I saw on the Professor Barber's presentations some graphs related to CAPEX, and I'm not sure about OPEX. Can you give a comment on it? Can you compare CAPEX and OPEX of hydrogen or for hydrogen vehicles and for competitive car type of vehicles?
Okay, thank you. I'm not the expert in CAPEX and OPEX, but I can give the opinion about general hydrogen infrastructure. It costs, yes, we have a high cost from investment and further in installation, but no one said it will be cheap. So I think the point of financial point for national question should not be the only reason to give up of hydrogen infrastructure, because for example it is currently much more expensive in comparison to battery for the station for electric vehicles for batteries. But if we, as I said, if we want to see more hydrogen vehicles on the road, we have to go with installation of hydrogen infrastructure, and this is something what is written in directives AFIR. So we will be in obligation to install hydrogen refueling station every 100 kilometers in around urban cities and TNT corridors after 2030. So I think it is better to start earlier, rather earlier than later. And this is the reason, hydrogen infrastructure is the reason why we don't have more hydrogen vehicles on the road. So these are technologies that I already said has to go in the parallel. I don't know who is the expert in CAPEX and OPEX, so maybe you can give the opinion about it. I smartly switched off. Professor?
Yeah. Any comment on it? Or
maybe I can do a few comments. I think it heavily depends on the size and technology. Let's say recently we did some projects in the defense sector. If you are on a smaller scale, certainly it's currently much more expensive than other competing technologies. But let's say also there you have to consider other benefits. I think, you know, there they go to the resilience, then they go to on-site energy vector production, and so there are multiple benefits. Which not in all sectors are present, but why I want to address this, that it's not wise to operate with a single number across the fields. So someone should really always look in specifics of a case, let's say some, I don't know, some island populations, some specific use cases, and there certainly these are best promotion scheme, promotion spots, where then you further develop technology, economy of scale goes up, prices go down, and I think this is the wise approach, not just saying currently it's more expensive, it's not viable. I think this is very wrong. So now giving a single digit that's valid for all around the world is not good. And also another thing is, when someone will build renewable energy system, there will not be one size fits all. If someone looks to Norway, certainly their renewable energy system in the future will look very differently, like in Croatia, like in Slovenia, like anywhere else. And someone should not just take the numbers over there, someone should really go into specific of the energy sector, calculate its own case and then see what are the benefits. And I think this is very important, not to just transfer the numbers.
Thank you. Professor Takani, you mentioned different kind of fuels which could be used in ships in 20 years, and you didn't predict future. You just well mentioned, okay, we should change it, but how we will do it? On what will be the choice? Can you try to predict at least? We will not make quotation or citation on what you will say now in 20 years or 30 years. Yeah.
Yes, thank you. Well, I want to start with an example, with an experience. Around 2010, liquid natural gas was considered a fuel, an interesting fuel for shipping. Not all the shipping community was convinced on that, because it was really a difficult challenge. Shipping is a sector where safety is at first, so having a fuel that has a low flash point was a problem. Anything lower than 60 degrees Celsius was not allowed on board. So think about flammable gas was something really almost impossible. Okay, at the end, 15 years later, LNG, liquid natural gas, is used on board. Ships sail, come to Trieste. I imagine they come to Dubrovnik as well. So you see that the technology issues can be overcome. Well, in that case, obviously there was the pollution problem. So the International Maritime Organization set some limits for sulfur, for nitrogen oxide, and so liquid natural gas could offer the possibility to meet these new limits, lower limits. But then the driver was another, that LNG was much cheaper than HFO, than the other fossil liquid fuel that were used on board. So the ship owners, for the ship owner was quite easy to decide, okay, I install LNG because the operation cost will be lower. Well, with hydrogen and hydrogen carrier, the story is completely different. Obviously, we can benefit from the experience of using a cryogenic fuel on board, such as LNG, so that the way to install liquid hydrogen on board will be easier. But again, we are talking about 100 degrees Celsius of difference, or 100 Kelvin. So liquid hydrogen on board is still very difficult, but today we have, for example, a ferry on a short route that sails using liquid hydrogen. So you see that this technology gap somehow was covered, and today we have this ferry that sails on liquid hydrogen. And we have other ships that today sails on methanol, for example. Methanol, it is easier to use. Internal combustion engine can be used, and so therefore I think that on shorter route hydrogen is a very good candidate, but for big ships such as a container ship on longer routes, maybe other hydrogen carrier can be developed or can be used. And at the end, what I see is that probably that there will be a mix of different fuels depending on the specific application.
Thank you. Professor Barbier, is there any real space for trains on hydrogen? So trains which are using hydrogen as fuel?
Yes, absolutely. As I said, even now, presently, on the lines that are longer than 100 kilometers and not electrified, it's cheaper to use hydrogen train than a battery train. Again, it also depends on configuration. For example, for this road from Split to Zagreb, we have a very high steep at the very beginning. So if we had a battery train, it will deplete all the batteries by the time it came to Labin, which is only 10 kilometers away from Split, because it's a very steep. So there is a probability for combination of those, but I'm pretty sure that the hydrogen does make sense for this from Ostaria to split. There is another line from Koprivnica to Osijek that is also not electrified, but that one is much easier to electrify because it's in a plain terrain. And then there is another one that is shorter than 100 kilometers, but very interesting for a touristic reason, and that's in Istria. They have a train in Istria that is now not even functional, but that could be revived and use hydrogen and use green hydrogen as an advertisement for green Istria.
Thank you. So I think we are now ready for a few questions from audience. Is there any? Yep, please.
Thank you for the interesting presentations. Hydrogen production by electrolysis from water has been mentioned several times. That's a viable source. When that is done, oxygen is a co-product. What are the thoughts about using the oxygen effectively as a co-product?
Okay, I can give the answer. Currently, the market for oxygen is huge. And when you look at the analysis of hydrogen power plants and how to produce hydrogen by water electrolysis and using renewables, you will see that a return is much faster by putting oxygen on the market. We have industry that needs oxygen for their processes, but also we can use it in medicine, in fishing, and there is a really huge market, and this is a good question. Usually people forgot on oxygen during the analysis, but there is a money. So for investors, when you do such analysis for designing hydrogen power plant, you should also give the analysis of hydrogen, of oxygen. I had the opportunity to make pre-feasibility study for one huge company, and my team suggested them to do analysis of oxygen, and they told us, no, we don't need oxygen. We said, but think one more time because there is a market for. No, we don't need it. And days after, they called me and said, okay, please include oxygen analysis. We searched the opportunities and the internet and the current status, so we did it. Thank you for this question. It is important.
So as said, yes, for sure, what was said is okay, and there will be oxygen market, but also if you look for stationary application, if you already have, let's say, oxygen and hydrogen, and if you have fuel cell, you might use this oxygen in a fuel cell, thereby you at the same pressure increase the partial pressure of the oxygen, which means that if you want to gain high power, you don't need the energy for compressing the air, which increases efficiency of the system. But also if you go to combustion related devices, be it gas turbine, stationary combustion in furnaces, whatever, if you go to oxy-combustion of hydrogen, you don't have problem of nitrogen oxides. So also there, in stationary application, direct use of oxygen. So what you do, it's only you split by electricity the two molecules, and then you combine them back, and this is then quite efficient process. So also there, it's direct use besides the market that was addressed previously.
I would like to raise certain concerns. Maybe these are already well known, but I want to educate myself. Hydrogen, if you split water, that's very energy intensive. Methane reform is one of the best options, but there you also produce CO2. The second concern is hydrogen leakage is also something, the lightest element, so that also is quite possible, and it might lead to, particularly if it's related to IC technology, then there could be also possibilities of hazards. The third one is hydrogen embrittlement. you are always storing in tanks or even in the nozzles, or in those cases, formation of hydrides leading to embrittlement of metal is also possible. So these are the three concerns. Maybe it's already solved, but I wanted to just learn from you.
If I understood correctly, you compare the efficiency of the electrolyzers versus the efficiency of steam reforming natural gas. If we are talking about decarbonization, that steam reforming of natural gas is out of question. We should not be producing hydrogen from natural gas to replace natural gas. Efficiency is a very efficient process. Efficiency, theoretical efficiency is 100%, and you can have an electrolyzer that works at 95% efficiency, except it's going to be large. So the efficiency of electrolyzer is actually a function of the price. Right now, industrial electrolyzer is about 66 to 70% efficient, because that's the optimum point between capex and opex. Your second question was on hydrogen leakage and creating a greenhouse gas, is that? Yes, that is an issue that is being investigated now, and hydrogen embrittlement is a problem with only certain pipelines. Certain ductile pipes, steel pipes, are prone to embrittlement, but that can be solved with a liner inside the pipe, with a polyethylene or some other plastic, a liner that prevents hydrogen going into the pipe. And not all the materials are prone to embrittlement. And that has been already taken care, and there's a whole industry that is making pipes for hydrogen that has this liner inside to prevent hydrogen going into the metal.
Maybe I agree with you. There are a lot of challenges still to be solved, so therefore it's not yet there in full extent. But I think also what is very important, as Professor Barbier said, is how to look in the future. I would say when I was in discussion at the site of European Green Vehicle Initiative, when they agreed on the next work program with European Commission, there were a lot of discussions how much we have raw materials, which are the technologies, and how it might not be possible to get to 250 due to several constraints. And then a man from a commission said very wise things. So you cannot look in 2050 with the technology of 2020. So we will put a lot of investigations in, we will put a lot of money in, and in 30 years or in 20 years, there will be a lot of progress. So I would say, I agree, there are currently quite some, let's say, challenges. I would by far not dare to say there are obstacles, but I think with future further developments, many of them will be resolved, but also maybe there will be some slightly different pathways that we can imagine them now, because the technology will lead us in this direction. So I think we should really be open in that kind and not be blocking the things. So, but yes, certainly there is a lot to solve still.
Other questions? If there are any. There on the back.
Safety-related question. Hydrogen car in garage with leakage of hydrogen. How dangerous it is?
Okay. Hydrogen leaks in a closed space, such as a garage, can be an issue. Hydrogen behaves very similar to natural gas. So hydrogen is lighter than air. It doesn't create a layer at the bottom. Hydrogen goes up. And the studies that have been done so far, both modeling and experimental studies, have shown that in any space that has any kind of ventilation, including even natural ventilation, it is practically impossible to create a flammable mixture of hydrogen and air. Hydrogen is flammable between 4 and 75%. You can create 4% of hydrogen, more than 4% of hydrogen concentration if there is a leak, and only about 30 centimeters above the leak, concentration will be more than 4%. Everything above that is a bit less. But if there is no ventilation, then yes, a cloud of hydrogen can form at the top, and then there must be a ventilation or a warning like we have now. CO in the garage is more than acceptable level, but I don't see that as a problem. There were a lot of studies also, hydrogen in the tunnels, and hydrogen in a closed space, but I don't see that as an obstacle.
Thank you, Frano. I just want to say that the comment of Professor Barbi was correct. So we have the experience of natural gas. For example, in Italy, we have a great number of cars running on natural gas. There are some limitations, obviously, in using natural gas, but these cars are running and are used. And again, probably hydrogen is a very good choice for energy-intensive transportation. Maybe for shorter distance, battery is an option. But again, battery, unfortunately, can be dangerous as well, and we had already some problems with the battery cars.
And I would also just add, if we imagine that there is a flammable concentration of hydrogen and that it caused explosion, the flame of hydrogen is going up. We didn't show, there is also video and a test on this issue, and if there is explosion, we will just see the flame going up, and it will go on in a few seconds, and your car will stay safe. So in comparison to today's commercial vehicles, you will have a burnt vehicle for combustion engine, and you will have your safe hydrogen vehicle. So it can happen, but it is so, I would not say impossible, but it is hard to get concentration, flammable concentration. Do you remember, Professor, the test of two cars in a 60 seconds?
Maybe if I might add, let's say, just on this, someone should also consider at which pressure level hydrogen leaks. Let's say if you're in the car and if you're at 700 bar, you have a highly supersonic flow. So, okay, it might cause combustible mixture, it might burn, but it will only cause flame. So it will not penetrate back in the tank. And when this will happen, the tank is nearly empty, and due to these thick lines, you will be quite safe. So let's say this is some concern in some, let's say, crashes. But okay, where it might get dangerous is when there are really, when you, let's say if you're in defense application or military application, or if you're a severe crash where you will, let's say, smash the tank, where there will be some ignition point, then yes, a lot of hydrogen can burn at once. But otherwise, let's say if there is just penetration or leak at very high pressure, it burns, but there is very low probability of severe explosion.
Okay, there is another question there. Yeah, please.
Thank you. So we have a question from audience on YouTube. From the point of view of developing countries, which technology for hydrogen production is most suitable?
I would say it depends on the country, it depends on geographical position, but the recommendation is to use renewables to supply electricity and to produce hydrogen by water electrolysis wherever it's possible. So, but we are starting for renewables. I think this is a starting point for each country, and later see if it is electrolysis, if it is a waste, or some other technology.
Thank you. Okay, we do have time for very short take-home messages from our panelists. So please, Professor Barber.
For me, this is like a dream come true, what is happening now with hydrogen. I've been working for 30 years, and I have always been ahead of my time. I told people I work on science fiction. They would say, oh, you're a writer. No, I'm not. I'm creating the science fiction with hydrogen. But now hydrogen is not science fiction anymore. We talk about hydrogen in the forums like this and many other forums. We have now this big project, North Adriatic Hydrogen Valley. We have many projects that are being intended in Croatia as well as in entire Europe. We have a budget of more than €1 billion in Europe for hydrogen projects. So this thing is happening. And I've been in my career through a lot of ups and downs, of high expectations and then big disappointments. I think we are now at a very high level of high expectations from hydrogen. This is, I think, one of the last opportunities. If you don't use this opportunity, something else will take it.
Okay, I would say that there is no question if hydrogen will have a role in this energy transition and decarbonization process. It is just a question in which amount we will have hydrogen in a particular sector, because this energy transition, now it's obvious, will not work without hydrogen. Thank you.
Maybe since I started with digitalization, I will also end with it. I would say exactly as a follow-up of this is very important that, let's say, we really have very good virtual tools from designing renewable energy systems for correctly placing all energy vectors, so not imposing them by, let's say, some partial knowledge or even by some specific, let's say, stakeholders, but that things are really well calculated in advance and that we really then well plan. And let's say then it goes further down that we well design systems and then we well control and monitor systems, and then it goes in the feedback with all this knowledge. We then try to feed the planning tools. We will not solve all this also in North Adriatic Hydrogen Valley, but we have also a few tasks exactly on this, that in the region, Italy might be an exception, but let's say Croatia and Slovenia, we don't yet have large production facilities. But it's also very important that we don't just buy a electrolyzer and a fuel cell, but there are different electrolyzers, there are different fuel cells. They have to be properly integrated in the system. We should monitor them and then gain knowledge which products to buy, how to operate them, how to integrate them, and this significantly at the end influences the cost. Currently, people still think that there are these Lego blocks which are, let's say, fully compatible and that someone does not look into it. So I think this high-level knowledge will really need to have a lot of further digitalization, data processing, thinking, and this is also the knowledge that we have to develop in the region. And I think with all the synergies that North Adriatic Hydrogen Valley brings us, we will also there do a boost, not also between us who are from the academic community, but also to bring this knowledge to the industries which were not yet acquainted with the hydrogen.
Thank you. Yes, I want to start from what the other panelists said. First of all, for me too, is somehow an emotion to see that in Trieste we are installing in the next month one electrolyzer, one big electrolyzer, and it is, it is something that sometimes I think, is it true? Because it is it is 30 years now that I'm working on hydrogen, but it is happening. But at the same time, we have to be realistic, and as Professor Katrasny said, hydrogen is only a part of this shift, of this energy shift. And even if this electrolyzer in Trieste and the other in Croatia and in Slovenia that will be installed, in Trieste, for example, we will produce 400 tons of hydrogen per year. So it is true that the energy content of hydrogen is 3 times more or less natural gas or oil. So it means that it is about 1,000 tons per year of hydrogen. A ship in one day consumes 25, 30 tons. So you see that it is nothing. But it is a starting point. Hydrogen will not solve all the problems. We have to focus on fundamental research on renewable energy. There is quite a lot of a way to improve and to increase the efficiency of the overall system. And still, hydrogen is very expensive. And again, energy planning, as Professor Katrashnik said, it is very important. We cannot let's say, waste energy because we don't use it the right way. We have to plan in advance and how to use this energy, and not only at the design point, not just that we have a plant, we need 500 tons per day and so on. No, we have to plan at part load operation in all and the cross-sector integration is very important. So transportation, hard-to-abate sector, it is important. We have to plan, and digitalization for this aim is, I'll say, essential. Thank you.
Thank you once again for a very nice presentation and discussion. So we are about to end this session on hydrogen.